Hello everyone. Today we are going to analyze this beam using consistent deformation method. In this beam there are two spans, span AB and span BC. In the span AB there is uniformly distributed load 36 kN per meter. It is acting for the whole span. In the span BC, there is a concentrated load 72 kN. It acts at a distance of 2 meter from the support B. Span AB is 4 meter long and its moment of inertia is 2I. Span BC is 6 meter long and its moment of inertia is I. Now let us find the degree of static indeterminacy. The number of unknown reactions and moments are three. They are the vertical reactions RA, RB and RC. The available equilibrium equations are two. The degree of static indeterminacy will be 3 minus 2, so it will be 1. In the previous problem, we have analyzed the same beam. There I released RB, but in this one, from the point B, I am going to release MB. When we do that, the continuous beam becomes two separate, simply supported beams. We know the equation which we are using in the consistent deformation method. We can take delta on the other side, so it will come downwards. In the point B, there is no other rotation or any other external movement, so delta will be 0. P will be the moment which we released, that is MP. So for MP, we will get minus delta L upon delta. First, I am going to find delta L, which is the displacement due to the loads. From the point B, we have released MP. So delta L will be the slope in the point B, which is theta B. To find the slope in the point B, we can use the conjugate beam method. In the conjugate beam method, we have to draw moment upon EI diagram. First, let us take the simply supported beam AB. We know that in the simply supported beam, uniformly distributed load is acting for the whole span. The formula to find the maximum bending moment is WL square upon 8. Here W is 36 and L is 4. So that we will get 72. Let us find moment upon EI. M is 72. The moment of inertia is 2I. So instead of EI, we have to apply 2EI. In this way, we will get 36 upon EI. Since it is UDL, the diagram will be in the shape of a parabola. Now let us take the beam BC. We know that if in the simply supported beam there is an eccentric point load, the formula to find the bending moment is WAB upon L. Here W is 72, A is 2, B is 4 and L is 6. We will get 96. Moment upon EI will be 96 upon EI. Let us keep this point as A dash, these 2 points as B dash, and this point as C dash. We need to find the reactions RB1 dash and RB2 dash. This conjugate beam is symmetrical, so we can easily find the reactions. RA dash and RB1 dash will be equal to the total area upon 2. This is a second degree parabola. The area formula is 2 upon 3 BH. Here the breadth is 4 and the height is 36 upon EI. So this is the area. When we divide the area by 2, we will get RB1 dash, which is 48 upon EI. Now we are going to find RB2 dash. This diagram is not symmetrical, so it is not very easy to find RB2 dash. To find RB2 dash, we can take a moment about C dash. In this case, we have to follow right hand side rule. Clockwise will be positive. and anti-clockwise will be negative. RB2 dash is acting in the clockwise direction, so that it will be positive, and the distance is 6. So 6 RB2 dash. The UVL is acting in the anti-clockwise direction, so that it will be negative. For the UVL, we have to multiply the area with the centroid distance. This is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is 6 and the height is 96 upon EI. So this is the area for this kind of triangle. The centroid distance about the right is L plus B upon 3. According to the formula, L is 6 and B is 4. For RB2 dash, we will get 160 upon EI. We know that delta L is the theta B, which is the shear force at B dash. The shear force at B dash is RB dash. We have to add these two. After adding, we will get 208 upon EI. We have found delta L. Now we are going to find delta. Delta is the displacement due to unit movement. We have to remove all of the loads from the beams, and we need to apply unit movement at B in the direction of MP. Let us assume that MP is a hugging movement. In AB, it would be acting in the clockwise direction, and in BC, it would be acting in the anti-clockwise direction. In the beam AB, using left-hand side rule, we can find the bending moment at B. In the point B, we have unit movement which is acting in the clockwise direction, so that it will be negative. And in the point A, the moment will be 0. Then in the point B, we can find M upon EI. M is minus 1 and EI is 2EI. Since it is negative, we have to keep UVL upwards. In the similar way, using right hand side rule, we can draw this diagram. Since the UVL is acting upwards, the reactions will be acting downwards. We need to find RB1 dash and RB2 dash. To find RB1 dash, let us take movement about A dash. RB1 dash is acting in the clockwise direction, so that it will be negative and the distance is 4. The UVL is acting in the anti-clockwise direction, so that it will be positive. For the UVL, we have to multiply the area with the centroid distance. We know the area formula half into BH. Here the breadth is 4 and the height is 1 upon 2 EI. So this is the area. The centroid distance about A dash is 2 upon 3 into B. Here the breadth is 4. So 2 upon 3 into 4. In this way, for RB1 dash, we will get 2 upon 3 EI. To find RB2 dash, let us take a moment about C dash. In this case, we have to follow right hand side rule. RB2 dash is acting in the anti-clockwise direction, so that it will be negative and the distance is 6. The UVL is acting in the clockwise direction, so that it will be positive. For the UVL, we have to multiply the area with the centroid distance. This is the area and this is the centroid distance. About C dash, the centroid distance is 2 upon 3 into breadth. Here the breadth is 6, so it will be 2 upon 3 into 6. For RB2 dash, we will get 2 upon EI. Now let us find delta, that is the slope in the point B, theta B. In the conjugate beam, theta B is the shear force at B dash, that is RB dash. We need to add both of these. Since they are acting downwards, both of them will be negative. For delta, we will get minus 8 upon 3 EI. In this formula, we have found delta L and delta. Let us apply both of them. We can eliminate negative and negative. Finally, for MP, we will get a 78 kilonewton meter. We have got a positive value. That means our assumption is correct. MP is a hugging moment. Now let us take the real beam. Using MP, we can find the vertical reactions. To find RA, let us take a moment about B. RA is acting in the clockwise direction so that it will be positive and the distance is 4. So for RA, the UDL is acting in the anticlockwise direction so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. About the span AB, MP is acting in the clockwise direction so that it will be positive. For RA, we will get 52.5 kilonewton. To find RC, let us take a moment about B. In this case, we have to follow left-hand side rule. RC is acting in the anticlockwise direction so that it will be positive and the distance is 6. So 6 RC. The point load 72 is acting in the clockwise direction so that it will be negative and the distance is 2. MB is acting in the anticlockwise direction so that it will be positive. For RC, we will get 11 kilonewton. By applying this rule, we can find RB. Now we are going to draw the bending moment diagram by superposition method. For that, first we have to draw the free movement diagram. We have to consider every span as a separate simply supported beam. Then using these formulas, we can find the moments and draw these two diagrams. Then using the moment at B, we can draw the end moment diagram. Combining both of these two diagrams, we can draw the bending moment diagram by superposition method. Using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment for AB. We can make a section in this point and find the distance. You can see that in that point, I have made a section at a distance of x from A. We know that in this section, the shear force is 0. Using right hand side rule, we can find the shear force. For x, we will get this. Now using the right hand side rule, we can find the maximum positive bending moment. The points A and C are the simply supported ends, so the moment will be 0. Using the right hand side rule, we can find the moment at B, which will be minus 78. We have already calculated that. Now let us use the left hand side rule and find the moment at D. RC is acting in the anticlockwise direction so that it will be positive and the distance is 4. For the moment at D, we will get 45.6. This is the proper bending moment diagram. If we make this diagram upside down, that is called the bending moment diagram on the tension side. In these 2 points, the bending moment becomes 0. These are the points of contraflexure. We can make sections in these 2 points and find the distances. First, let us find the distance in the span AB. In the span AB, I have made a section at a distance of x from A. Using the right hand side rule, we can find the distance. Now let us find the distance in the span BC. I have made a section at a distance of x from C. Using the left hand side rule, we can find the distance as 4.72 meter. Now we are going to end this session. Thank you for watching.